course, I went through the graphs last day. There was something I did not get to do it here. Right. So in a simple pendulum, I want you to remember I was supposed to show you how to derive this formula here. Right? Okay. So let's take a look at how to determine how to show if an object moves with simple harmonic motion, right? So if you look here, there are some steps that we have to follow. Step number 1, yes. Right? So here's what you have to do. To determine if a body moves with simple harmonic motion, there are 3 nice little steps that we have to take. And I'm going to show you by an example, right? First, you have to draw a diagram. With the body at the arbitrary displacement x from a position O. So imagine you have a pendulum here and it displaces some distance x. You have to show that, right? Then on the diagram, marking all the forces acting and determine the resultant force in directional displacement. Right? Then step number 3, use Newton's second law to determine the acceleration A. And if it's in that form, we know it has simple harmonic motion, right? So I am going to apply those 3 steps in this example here. Everybody okay with that? So I'm going to show you where all these things come from, right? Right, so let's just catch that there. Going back on the whiteboard, right? Actually, if you don't catch, right, I will change it slightly. Right, our objective is to do these 2 things. Our objective is to do that last thing there. T is equal to 2 pi by the square root of LG. I can do it now. So we are trying to show that a pendulum moves in simple harmonic motion and then find the period of that object. Okay. So I'm giving you an object. This is the equilibrium position. So I am displacing it at distance x. The angular displacement here theta and the length of the string is L. Right? Well, what are the forces acting on it? Sorry? And you have tension, right? Right. There is a resultant force. If I were to leave it here, Kevin, if I were to leave the pendulum right there, what would I say? Would it stay right there? No, it'll go back where? So go back. So therefore, it must be a resultant force acting in that direction. Correct? Yeah. So we draw a diagram and put in the forces. Now we apply Newton's second law. The resultant force is equal to mass by acceleration. You know that, right? But the resultant force in this case is a component of weight, right? Pulling it back that way. And the component is mg sine theta. But I'm going to put a minus sign because it's acting in the opposite direction. So minus mg sine theta is equal to me. What would happen here to the m's? Right. So you're going to get minus g sine theta is equal to a. I just switching it around, right? A is equal to minus g sine theta. Right. But you all remember that theta is always be small when you're doing a pendulum lab and you always tell them make theta small, right? So since all right, before I do that, I will just show you this from right here. Can I find sine theta here? Sine theta is what? Opposite over hypotenuse. You okay with that? Yeah. Sine theta is opposite over hypotenuse. So can I take that off here? So I'll get A is equal to minus G. I'm taking off sine theta and I write in x over L. What's the objective of this right now? I'll write it. That's not possible. It's in the handout. What's the objective of this whole thing? To get a period. Right. To show that it's moving with simple harmonic motion. And simple harmonic motion means what?
Yeah, sorry.
And it take place in opposite directions, right? Right? And it take place in opposite directions. So A, if you remember simple harmonic motion, you should be able to write the formula like that. Okay? Everybody okay with that? Yeah? So watch this here. Can I write this in that form?
Yeah. Yeah.
Y'all see that?
So,
So from this here, what to do?
A will equal to negative G over L multiplied by X.
That's okay? Jacob? You see that? So Jacob, so we've seen it here, right? We see A is proportional to minus X. Y'all seeing that? So therefore the object has simple harmonic motion. Bob, could you tell me what G and L equals to? Look at the formula there.
So,
Watch this. Omega squared. Right? So you would recognize omega squared is equal to G on L. So omega is square root of G on L. Right? And remember the objective of this exercise? To find period. Period is what? Period is 2 pi over, and we found omega here. So period is equal to 2 pi over root of G on L. If you flip it up, you watch a video.
It is a square.
Very good. Right? So what you have there? Period. Okay? So if an object is moving with simple harmonic motion, which a pendulum does, that's the period. Okay? You have to be able to do this in proof, right? Copy now.
What time is it? After class, huh? Yeah, I didn't give answers to questions.
Somebody else. All right, so that's how you show simple harmonic motion, right? You draw a diagram, putting all the forces, applying Newton's second law, and then try to rearrange and make it in the form A is proportional to minus X. Jacob, please. Just be careful. I don't think you care of that. That's awesome. They didn't know that failed just before.
Yeah. You don't have to get out there. Please you.
Are you ready?
Yeah, I know something right there. I know something. I know something right there.
Here's the again. This is to show simple harmonic, right? Also, if they ask you to prove T is equal to 2 pi root ln, this is what you have to do. This is what you got. Now done? Right, now I have a little question for chocolate here. What would happen? Why is it all the oscillations are not free oscillations? Which money? Huh? Why is it all oscillations are not free oscillations? Because of damping here. Correct. Wait, chocolate here, boy. Right? Yes, because of damping. Right? Because there's damping and there's that loss of energy. Nice. Huh? Yeah. Right, so I'll give our next one. Okay, back to the handout, right? Right. So what you see in the handout, right? In the handout, we talked about remember this graph? Yeah. Right? And that graph applied to what? That graph applies to free oscillations. Right? The total mechanical energy constant. Excuse me, you can do that later. On your message. Make a note. Right? So yes. So an object with simple harmonic motion in a free oscillation behaves like that. All right. So it has kinetic, it has potential, and the sum is constant. Right? So therefore, we should be able to write a formula for potential energy, write a formula for kinetic, add it, and get that constant on top there. So what you see, right? So if you look at this here, potential energy, for example, for a spring is your strain energy. Remember that formula? Strain energy. I have kx squared So if I were to substitute for K, you will get this version of the formula on the right here. You will get potential energy is equal to half m omega squared x squared. Right? So this formula here is potential energy. We know what kinetic is. Kinetic is a half mv squared. If I put this in here, it simplifies to this. When you add it, you'll get that. That make any sense?
Okay.
Nah, that makes sense. So what you saying? I'm going to show you on the code. Right? So here's what we're saying, right? We are saying for something moving with simple harmonic motion in a free oscillation, we know that the total of the kinetic plus the potential is constant. So you want to show that, right? Potential energy is equal to half kx squared was one version, and we also know that omega is what? Right? Omega was equal to k on m. Okay, so k is equal to omega by m. So if I substitute k in there, I'll get potential energy is a half m omega x squared. That's okay? That's the potential energy of something moving with simple harmonic. So we find potential energy. Let's find, we found potential energy. Let's find kinetic energy now. We know that kinetic energy is equal to half mv squared, and you know there's an error. It should have been half, right? A half mv squared. We know that v is plus or minus omega by the square root of x naught squared minus x squared. Right? If I take this and I drop this in here, I will end up with kinetic energy being a half m. What would v squared be? If I were to square this, what would I get? You'll get omega squared by x naught squared minus x squared. So I'm going to put that here. That's okay? If I multiply this out, watch this now, right? Kinetic energy is equal to half m omega squared x naught squared minus a half omega squared x squared. You see that? This is kinetic. What is total mechanical energy? Kinetic plus what? So if I were to add potential is a half m omega x squared.
You get m omega squared x squared.
Right. All right, I'll check my data sound. But this will cancel, right? And you will end up with the total energy being a half m omega squared x naught squared. And what you see, any mass constant? X naught is the amplitude. That won't change. That's not changing. This constant as well. And n omega squared is a constant. So if every single thing here is a constant, what does it say? It means that the total energy will be constant. That's okay? Copy that down.
How you get the omega equal to 10?
Oh, this is supposed to be omega squared. Okay.
I get shucks because of this thing. It's that we spring.
Oh, it's another listener, yeah? Right, yeah, sorry.
Yeah, you get omega squared pretty good.
Yeah, there's some misspelling. This is the first example in the notes. Okay, so this is your total energy. So if they ask you to find kinetic energy, that's it here. If they ask you to find potential energy, that's this here. Of course, if you sum it, you should get this. Right? I made a mistake here, it's omega squared, right? So K is equal to omega squared by M. Correct me handle, but I made a mistake. Finish. Yeah, I think I just added me in there. I know if you're listening.
Yeah, thank you.
Yeah, you know, so. Quiet. So that's like you have all this already? Speak up, you have all this already? You're writing wrong thing. So we putting on a plan about the last way. I still have money. You will have come for you. All right, so. Big on Google here. Are you working it out? All right, nice. All right, so again, so that's something that's great to remember about simple harmonic. Let's just talk about damping and then we can try a question. Hold on to. It's fine. You can show you do one. Yeah, sorry. No? All right. A real good one. Yes, Katrina, Nathaniel. I don't know if it can fit now yet. It's exclusive. It might get attention of this. Huh? What's Peter? Huh?
Yes, sir.
She'll tell it, just message the admin and she'll tell it. Huh? All right, ready? So what do we need? What do we need? Last thing I want to talk about before I jump into any questions, I want to just talk about damping, right? What does damping do in income? Huh? It takes energy out of the system. So what will I do?
So I find it out.
What will I push my coin in for?
So you call the name of that.
I remember. I don't remember that one. I forget. Right. So damping, right? So whenever we take energy out of the system, it means that the system has to do some work against some kind of resistance. That resistance is what we call damping, right? So damping is the process in which energy is taken from an oscillating system to do work overcoming dissipative forces. All right? Dissipated forces. A damped oscillation is one in which the amplitude is reduced as a result of the energy of the system being reduced by dissipated forces. So if you look here, here is something that is not damped. How do you know that?
So because the amplitude is the same.
The amplitude staying the same over time, right? Look at the likely damp. The amplitude is a gradual decrease. But why the amplitude? Why not something else?
So because the amplitude is the how much in space. So if there is a resistance in the space that much.
A close state, but look at the formula I showed you all here. And this is total energy.
Oh, so if everything remains constant, right? The amplitude, if the amplitude
Gets smaller.
gets
Right.
smaller, then
So if omega squared state is a constant and m is a constant, right? Then if the amplitude gets smaller and smaller and smaller and smaller, then the energy available for the system gets smaller as well. Right? Well, vice versa. The energy is smaller, so therefore the amplitude will get smaller. Right? So this here is light damping. This is what you will experience in the lab. Correct? If you allow the pendulum to oscillate, it'll behave like this. Then you have, right, period remain the same and so on, right? Then you have heavy damping and critical damping. What you recognize about critical damping when compared to heavy damping? Sylvester.
Yes, sir.
What do you think? So, what's the damping?
Yeah,
Who dampened up? There you go. Right? So, what kind of damping is that, Sylvester? It didn't reach here. So, what kind of damping is that? Critical or heavy? Heavy damping. You all recognize what's heavy damping? Heavy damping, it doesn't come back to the original. What? Recognize that? So Jacob just creates heavy damping. Right? What does critical damping do? In a very short space, critical damping allows it to go back to the original position. When do you want that to happen? Think about real life application or apparatus that you want that to happen in. Critical damping. Huh?
what?
Okay, open and it's right back. I find like in a car shops as well. You know when the car oscillating it,
Yeah.
when the car hit a pothole, you want it to go right back to the equilibrium. You don't want it oscillating. Right?
Be critically dampened, though.
You sure you don't want heavy?
Yeah, you sure you don't want
Heavy damping will never come back.
Yeah.
Look how long it taken. Look how long heavy damping taken to reach back. Right? So heavy damping might be like on the moon, you go up, take forever to come back down. Okay? So critical damping is where you don't want any oscillation. For example, you have taken an ammeter reading. Do you want your needle? Do you want your needle to be oscillating? No. You want it to be critically damped. Right? So the system is damped so that it just fails to oscillate. That is no real oscillation, right? That's critical damping. The time taken for the displacement to move from maximum to zero is a minimum. It is used in shock absorbers in cars, which are damped just before critical damping. Pointers and pointers, right? Pointers in moving coil galvanometer.
What about like the roller coaster? You really drop you once.
Huh?
Drop your roller coaster.
No, and that's oscillates.
No, but what I just drop. This one not going back up.
I even now going back up with a total by example. Right?
No.
Overdamping, the degree of damping is greater than that of critical. Then the system is heavily damped. The return to equilibrium position takes a long time. So, question, how do we overcome damping?
So yeah, driving
Add a driving force, yes. Add a driving force, right? So if your pendulum stop oscillating or slowing down, the natural thing to do is to what?
push it.
Apply a force oscillation, right? But here's what. There is a special thing that happens that when, look at the underlying part. When the force that you apply, oh wait, no. underneath here. Right? When the frequency of the force you apply is equal to the frequency of the object, a large oscillation is obtained. Right? That is something that we call resonance. So resonance is when you match the frequency of an oscillating system. You would recognize it's oscillating with a larger amplitude. So watch this here. I want to show you a small example, right?
So you think you could like something like you think you can do it?
Right? You'll ever use the you all think you ever experience resonance?
Yes, sir.
Right? You'll ever blow in a bottle
Yeah.
and then hear a loud sound. That loud sound is a resonance sound. It's of a larger amplitude. But remember, and you have to blow in at the right frequency. If it just started blowing that's like that, you wouldn't hear anything. Yeah, when you're blowing in a glass, when you hear that loud sound was a resonance sound. Right? You know what they did tuning for? Loud?
We did.
Where you have a little fork and then at a particular frequency you hear it loud? Right.
Yeah.
That's technically resonance. The frequency that you create matches a natural frequency and you get that loud sound. Right? There is a very popular experiment called a simulation called Barton's pentacle on it. I wanted to show you it real fast. And tell me why it's happened, right? Well, what put you here for it? What can I tell you? All right, so watch this here. Right, here's an example of resonance. Right, see if we can explain what happening here. Online, you'll see the screen. This should be a small video, right? I'm gonna try and play. What you set up there. So you have a this is a driver force here. We're gonna move this, right? What we call, and you have 1, 2, 3, 4, 5, 6 pendulums, but the pendulums at the different heights. Watch what is going to happen. All connected, all connected. Watch what's going to happen, right? Hopefully you don't talk too much, right? Online, you'll see the video. Like mine.
This video for Animated Science. It's Wednesday, 21st of September.
Yeah, shaking on it, that's all. I'm just not the destination. Online is moving. Right, see, all have different like cavity quick on that. That's true there. Right, they all connected, right? They all connected. You go to this place in driver this now. And look at what happened now. I to explain why it happened. Manuel, watch it here, watch it here, watch it here. Wait, there's something special going to happen. There's something behind. It's still moving a little faster. Right, watch it now, watch it here. What you observe happening? Which one? Only one moving the same speed, you recognize that? Only one moving with a larger amplitude. Amplitude, right? So only one has a larger amplitude. You recognize that?
Yeah.
Right? Why? So what wavelengths? Right? Only one moving. That particular one alone is moving. Why? Well, obviously, I'm showing you an example already. But why? Why?
Say,
I like that.
driving frequency is equal to national frequency resonance.
Right. So the driving frequency of the ball was equal to the driving frequency of the ball was equal to the natural frequency of this one, right? Why? Why? It has six pendulums there. Very good. Somebody say two of them are the same length. So they have the same frequency. Here's why. You all remember this formula? T is equal to this 2 pi by the square root of LMG. Right? So the only factor controlling period here is what? Length. Right?
Yeah.
So if the length is the same, period is the same. And if period is the same, frequency is the same. Because frequency is going on. Everybody okay with that? That's the reason why that's the only one that's move with a great amplitude. Online, are you okay with that? Well, I know Katrina listening for this. Katrina, you okay with that? Rihanna? David didn't listen. Rihanna, you okay with that? Okay, so that's the concept of resonance. That's the concept of the driver force. All right. Okay. Just take a look at this graph here.
The last little box. The box where?
Monkey said, "Yes, you get no store, right. So what's this here? There's a graph that we have to learn, right? There's a graph that we have to learn. So if I give you a system, right? And I ask you to plot amplitude versus frequency of systems that are dumped at different levels, the graph will look like that. Right? I have a question, right? Why is the undamped looking like that?
Which one? The undamped.
Why is the undamped looking like that, but the lightly damped and the heavily damped looking like that?
So because when it's undamped, yeah. Okay, I'm not like
Right. So think of an undamped system. Do we need to add energy to that? So where you can add energy, power amp to the amplitude. Too big, right? But if you have something lightly damped and you apply resonance to it, and you will get a large amplitude, and then something heavily damped. Same thing, right? But of course, they would be lower. But I also want you to notice something, right? It occurs a little bit earlier. So the more damped the system is, the resonance frequency happens a little bit earlier. Why the under? See? Because if you add energy to something that already oscillating high, it will just oscillate at infinite amplitude. So they're trying to tell you that the amplitude is very large. Okay? So we have to be able to explain that graph. I want you to notice two things, right? As the damping increasing, the maximum amplitude decreasing. And the frequency is occurring at is earlier. All right? So I told you that this is a note here, right? Increasing damping reduces the value of the amplitude and causes the maximum amplitude to be reached when the driving frequency is less than the frequency system. That's okay? So it's happening earlier. Resonance will happen earlier. Right, Sylvester? What happened earlier? All right, nice. Okay, so that's the concept of damping and resonance. It has some examples here. You can read up on it. One of the examples that you have to remember is that in aircraft, right? Right? On aircraft, the tails and the wings were tested through wind tunnels. Sorry? What?
That I should do.
Probably no. Right? Must be tested in wind tunnels to ensure the force oscillations produced by the wind do not produce very large amplitude. So for example, your like plane's wing already oscillating. Everything oscillates, right? If, for example, the wind passing over it allows it to undergo resonance, the wing will oscillate too large. And if the oscillation is too large, the wing will be destroyed, right? Right? So it have good and bad uses of resonance. You all know how the microwave works?
Yeah.
It works with resonance, right? So microwave ovens generate a microwave frequency, which is equal to the natural frequency of the oscillating water wave at cilia. When the food is placed in a microwave oven, the water molecules present in the food resonate and absorb energy from the microwave, causing the food to become hot. That's also, you know, recognize when you put bread in the microwave, or something. Bread. No, but if you put it for a short period, it kind of gets soggy.
Yeah.
Why?
Because
Because all the water molecules, right? It's had across all the water molecules, but it becomes dry when what? When the water molecules get too much energy and leave, right? Right, yeah, you put it in microwave with prices. All right, nice. Let's do a question. Anybody can just look back and see if we did one last week. Oh yeah, we did last week.
2016.
I don't want. What?
Last week. It actually don't have paper balls. It comes from sleep.
Start here.
there's not so many.
So you can say, I think Jack and see what you know.
Try that in. You have some more. Put food together, right? Yeah, not chocolate. Two. Because money, tell the chocolate people that. Well, we pull it out, we still demand the vaca. Ready? Try that fast now. Wait, you mind doing one thing for the class? Just one thing. But anyway, you know what I enjoy? Silence. So I don't mind. Really enjoying that silence. Quiet and nice. Quiet today, boy. Why is it quiet today? Yeah, give. Eat a gift too. From the class will eat to until it's far away. After remember. Use Mr. Faith. Mr. Faith. Young Faith came in very late. No, why? But I can always send money camera for things. Well, I'll walk you up on. Oh yeah, try that fast and then we have a next one, 26, 2018 after.
So you're not adding camera, but then.
Okay, travel from where come on, travel.
Wait,
Right, most important in moving with simple harmonic motion, right? Calculate the maximum kinetic energy, right? Based on the formula there, maximum kinetic energy is what?
Omega square x naught square.
So maximum kinetic energy is a half m omega squared x naught squared. Okay? Because remember, maximum velocity occurs when x is 0. Catch it up? I'll change colors just for you.
No, you have to. No, when can I take off?
Yeah, what's up? Sorry. That'll be a half m omega squared x naught squared. Right, first one again, not chocolates. Again, not chocolates.
Chocolate.
I tell you, can I do the question, please? So you have mass. Please work in the right SI unit, right? You have the mass, you have frequency. Oh, wait, we do have. So you have
Push up, Omega.
stay quiet and let people think about it now. Sylvester will go on why. Do the question now.
So, yeah,
Right.
see?
But I will put it time to the question for money group, but kind of not putting control, right? I guess it's zero. Well done, message answer, let me finish. Message the answer if you are finished. Got you? Yeah. Let's figure it out. What you guys still best up? Yeah, the best up, where you in? Right, okay, so. Right, so let's substitute the value. The half is how much, Sylvester? Okay. What's the mass?
Mass.
10 to the minus 3, right? Right, we don't know omega squared yet. What is X naught?
3.0 by 10 to the minus 7.
What?
Yeah. Why, what's 3?
Alright. Right. How we getting omega though, right? We don't have omega, all we have is frequency. So omega is what? Right? Omega is 2 pi by frequency. So omega will be 2 pi multiplied by 4.5 hertz. How much is that? How much? 20.227 joules. Anybody else get that? 28.27.
Yeah, I did. So you looking for.
I get to know how to get down. Oh. I get 2 points in here.
How what
In
you
that
have?
10 to 4.
Yeah, I suppose.
So now I don't know.
So what? Oh, that's what you do. Oh, so we go into that.
Oh, wait, so what is that in kinetic?
No, you start, I think it's 2.0 by 10 negative 5.
Okay, now I see.
Wait, what's the final answer?
Yeah, now I want to know. Yeah, people do. 2.0 minus 5.
I just want to go back up.
No, no, what the whole thing.
Yeah.
2.09 by 10 to the. Alright, nice. Oh, I thought I was wrong. 2.1 by 10 to the, okay, minus 5 joules. Okay, nice. Let's go again. This question has more tape, but I'm finding back the original one.
Yeah.
Anybody recognize it? Question. Yeah, I'm not finding back the original. Let's do 2018. Darian, are you there? Yeah. Yeah. Let's go again. Next one. Everybody write it. Let's see which one. Right, the first part of the definition, and then you have to write something, right? So the calculation. Twenty 18, yeah. Part D, number 5, part D. I can't really do it much more, right? Try this, please. 2018. Can't really help for you doing that. Ready? You see? Number 5, part D. Part A, B, and C is just definition. Sylvester, can you do something for me, please? Trying to get like Dario, eh? No diagram, no message, don't say nothing. He online then?
But I say I hear though.
Send one answer for me, please, diagram. Book it out, send an answer, please.
Hey.
Right, they give it the mass, they give it simple harmonic. Right? Right, they give it the period, they give it amplitude. Find the maximum speed. Right, so go to the maximum speed formula, book it out. And then find maximum energy. Two of them. We almost done last stuff. You can finish up and say it in one.
So I think hey, it's easy got the one that I did have to finish
One on that.
That's that.
Oh yeah, book it out fast. Just like the last one. Diane, it would be nice if you can message one answer, right? I don't even want two Diane, that's what one. Brianna, you follow what's going on? Okay, book it out. Don't forget to message your answers, right, Brianna? Please don't be like Diane. And finish. Right, do both one time, right? Find the period and then find the
Period.
oh wait, sorry, I went on the wrong one, sorry. Find the maximum velocity speed and the maximum energy. Yeah, let's go over. Alright, good. After that, we gotta find the period, right? So let's start here. They want us to find maximum speed. We know that maximum speed is omega x naught.
So that's. Because why would you find maximum speed this when you can just find, you know?
So that's 2 pi by 1 on 8. Somebody was saying something?
I think it was Sylvester.
So that's up. Bye-bye. Right, and the amplitude is 5. How much you got there?
2.93 per second.
3 point.
93.
Meters per second. So therefore, maximum kinetic energy will be a half mv squared. So that's a half by 2 by 3.93 squared. How much?
Period, one and a half.
Get up. Yeah, 3.93.
There you go. You get that?
2 pi, yeah. F is 1 on 8.
F is 1 and 8. So yeah, that we can find that.
And then what you got for kinetic energy?
So again, 50.421 joules.
13.4
4.
joules. Next, our next part. Last two parts. The mass is now attached to a string of length 2 meters. Same here, right? Same here. It is whirled in a horizontal circle, find its speed. Notice it is moving with simple harmonic motion.
So you can reach a
In part 1, is it moving with simple harmonic motion? No. So remember we did one like this last week? What do you have to apply here? Your circular motion formulas, right? Part 2, what you using in part 2? How you find the period in part 2? T is equal to what? 2 pi by square root of L on G, the one I did on board. Right? Because the object is moving with simple harmonic motion, right? That's the important part.
No, I don't feel it's well, that's. I don't want to think it up. I got you.
Move the. Sorry. Oh yeah, the last part coming down. Right? What we did in the period of Tilia, T is equal to what? Pi on omega, right? Pi again omega for circular motion, Javed. Yeah. Remember, it's not movement simple harmonic as yet, right? V will be equal to what? V is equal to IR. I think it.
Yeah, you did too many.
I like how you're bringing things together. Nice. That's really good. Right, V is equal to omega R. Yeah, one line letter, right. That was really good. Got it. Right, omega is C on R, right? It's out fast, omega. Right, and they give you everything, right? The speed is 5 and the radius is 2. Find the period. And then to the next one, tell me what answer they got. Part 1 and 2. Everybody follow what's going on? Yeah? Yeah, write it down.
No, but I can't think that is serious. Probably you're wrong.
Yeah, correct.
Correct?
Right, how much you all got for the first period, part 1?
2.5.
2 point,
5.
and then the second one, the formula is once again,
5 root ln cube.
right? So that is 2 pi by the square root of 2 over 9.8, right?
1.
What they give it to you, sir?
4.84.
Oh, that's they give us 9 point, sometimes it'll separate. 9.8 what? 9.81 is what they gave us.
368.
Yeah? What's the answer?
2.84 seconds.
Right, so the period increased a little, right? Okay, nice. So that is a simple harmonic motion. Right, next day we do all 1 or 2 more again, and then we start out. Then we start into the waves part of it. Okay, so we have waves to do, we have waves to do. Waves and length, waves to the longest. That's simple harmonic. That's on Darian, an answer. Good job, Darian.